This is the new cycle of cumulative effect that is hosted in EGP, the new EGP. And now, instead of looking at the not ring of fire, we're going to look at the real Abitibi. And the idea is to look at, spatial-temporal evolution of metal atmospheric emission in the environment. Why the Abitibi? Because there is a century of activity there that, it's a good thing for cumulative effect, for sure. Those are the project members for now. It's still, people want to participate, we're really open. The room and online know about metal in the environment back at the end of the 90s and beginning of 2000, which was a big scale program looking at different smelters around the country with an emphasis or a more detailed study probably around the Horn smelter in Abitibi. And so a lot of work has been done looking at different matrices, snow, soil, peat, lake, trees, etc. 100 kilometers around, but even more. And the usual suspects of metalloids at that time were arsenic, cadmium, copper, lead, nickel, and zinc, essentially. The focus was really on the spatial aspect of it, and what came out of it was that you have actually a signature of the smelter up to 60 kilometers downwind, and you had like a pattern downwind. There was a bit of temporal aspect that was covered, looking at tree rings. That was the onset of dendrochemistry, dendrogeochemistry with Martin Sarah and Joël, who is here. Oh, by the way, I'm not alone on this. Nicolas Benoit is co-leading, and Joël Martin as well. And so the tree ring showed there was a 15-year lag in between the signal coming into the environment and record in the tree. And in the sediments, a couple lake sediment were cored 9, I think, total, to be exact, like full cores. The results are non-conclusive, I think, to me, anyway. So this is where we are coming from. Today, the reason why we're looking at this again with a smaller team, we'll see what we can do, right? It's because the emission profile of the smelter has changed quite a lot. The feeding stock has changed. Already changed a little bit before the MITE program, which you can see that was in 2000. You have a big drop of all of the emission of lead, zinc, arsenic, copper, and cadmium, but then you still have something coming out after, and the feedstock has changed. We have no ore from the Horn mine anymore, or the Noranda mine, and we have other ore coming from everywhere on the planet, but also a lot of electronic recycling. And so in the electronic recycling, you have a lot of what is called emerging metalloids that you can see in it that are of economic interest for CLGD or for a lot of countries actually in the world, but also we have not really a lot of understanding of how they behave in the environment and also about their bigger toxicology, poorly understood for some of them. So this is actually what we want to look at. We want to change a bit the focus on metalloids, and we want to look at some of those emerging metalloids, especially the rare earths. And interestingly enough, there are a couple of teams in Quebec that are looking at that at UQAM, Michael Rosabal, and this is actually a student, Jeremy, who has looked at lichen on a transect going away from the Horn smelter, and you see a classic pattern of point source for different rare earths elements. So that there is actually something that you can learn from. So what we want to do, we've divided this in 3 sub-activities because that's an activity. We want to add this historical aspect on those emerging metalloids with an emphasis on those guys here, rare earths and all those guys. And we'll look at different archive again. We'll choose better our peat this time. And we'll see how those different compare, how we can actually see those metalloids in the environment. The second sub-activity is modeling based, but we'll need to take a lot of additional soil sample. We'll revisit some of the mite site to see how it has evolved over time. And the idea is to use this data to model the spatial distribution, and instead of a classic interpolation, to add some stochastic approach to it, to a better better constraint on the uncertainty. Some geostats and machine learning will be put in those models as well in order to integrate other parameters in it, such as, for example, wind direction. You see here, those are S-curves all around. The reason why they're here is because this next subactivity is linked to this one. Since it is the estimation of the recharge by stochastic means, in order to, again, have a better understanding of the recharge, and because the recharge is actually the potential vector to transfer of contaminants in groundwater. So, of course, there is no geochemistry here. This is purely the recharge and just looking at the recharge potential transfer of contaminant. The next step potentially, but this is outside of the scope right now, is to look at how reactive that can be. I think that's it.